Okay. Okay. So today we're wrapping up chapter 9. I'm going to limit, like what I was mentioning last week. I'm going to limit the amount of math that we'll do because I actually want to use this point as a transition into relativity. So specifically, the electromagnetic field of a moving charge shows this kind of compressed electric field and compressed electric field in the direction of motion. And that comes out of the Green's function, and that comes out of the concept of the those retarded Green's functions, but it's also completely consistent with the way that relativity works. So I think that's the point where we want to actually start thinking about E&M in relativistic terms. It's also one of those things that once you see it that way, you cannot unsee it. And certain things just make way more sense once you start treating them relativistically. So this is one of them. The other is the actual concept of the Lorentz force. So what I mean by the Lorentz force is the that force that's acting on a particle that's moving with some speed through a magnetic field. There are two things that always bugged me when I was first learning electromagnetism, back before you guys were born, most of you. So the first thing that was bugging me was the fact that there are cross products everywhere. So the first thing that bothered me about the Lorentz force was that there's a cross product. So most forces that we know are central forces. They are acting in a line that is joining the objects together. It is very, very odd to think about forces that are perpendicular to whatever it is that's causing it. But lo and behold, that's what the Lorentz force does. And I was never satisfactorily happy with the explanation, of course, other than, you could do the experiment and you can see it. But it didn't really make any sense until I actually started learning relativity. So, and the relativistic description of E&M, because then you will see that. The other thing that was bugging me was that same thing, but now with respect to the velocity. So you have some kind of a magnetic field, and you have a charged particle moving through that magnetic field with some velocity. What do you do in a field that is in a frame that is co-moving with that particle? Then your velocity would be zero. So then you would have no Lorentz force. Now, of course, so relativity says, well, if you have that magnetic field, if you imagine that field being generated by some kind of a current carrying wire, and then if you do a Lorentz transformation, there is length contraction, and that's going to be different for positive charged carriers moving in the wire versus negative charged carriers in the wire. They'll experience a different length contraction. And that means that if you have some kind of a current carrying wire that's generating a magnetic field, and you have some particle moving through that magnetic field, in a frame that is moving with that particle, it'll actually see a charged line. So that wire that first is neutral, then starts to appear as a charged wire, and now you have a charged wire, and then you have an electric field, and therefore you get a force, and that is the Lorentz force. So it is purely because of the length contraction that we get the Lorentz force. So I after these two things, I hope that I convince you that there is a lot of insight to be gleaned from looking at E&M this way. So rest of class, what we will do is we'll wrap up some things about chapter 9. I don't want to go too far into the weeds, but there are a couple of concepts that I need to point out to you because I'm supposed to. And then we'll start with relativity. Now, relativity. I'm assuming it's been a while, if at all. So we're going to start real slow with the time clock, and we'll just talk about time dilation and length contraction and twin paradoxes and all that stuff. So there is there's something about relativity, unfortunately, that is it is really, really counterintuitive. And it's not helped by the fact that we use terminology that is not very useful. So for instance, time dilation is usually the thing that we use to describe, okay, what happens in a twin paradox, right? So you have a moving clock, and that's moving, and then when it's moving, the clock slows down, except that's really not the right way to look at it, because it's really not the clock that's moving that is slowing down. It's you moving with respect to the clock that is changing your perception of time, because a clock at rest in some inertial frame is the most natural way to measure time. So, but in our nomenclature, when we decided to call something that's moving with a certain speed from us, we immediately started naming this with the twin paradox in mind, right? So we're at Earth, we send somebody off to, Alpha Centauri with a ridiculous speed, and then because the clock for this astronaut moves slower, which is not true, but it moves slower, therefore you have time dilation. But that perspective is wrong, and unfortunately, that perspective is still encoded in the way that we've labeled time dilation, and the same thing is occurring with length contraction. So just be mindful of those things, that we've tried to wrap our heads around things, and sometimes these terminologies, they can be useful because you can always go back to like, well, okay, how did we label these things? For instance, when we were talking about the twin paradox. But just keep in mind that it's not, the terminology itself is very, very confusing, and it's not helped. And then, of course, once we've done that, we will start putting some of the more formal mathematics into this. So we'll do but we'll probably do that on Wednesday. Okay. So let's wrap up some of the things, some of the dangling bonds that I left on the table. So when we have the Green's function approach to finding the potential of some kind of an arbitrary charge configuration, charge and current configuration, we have this triple integral. Oops, to D3. D3 prime, and then we're going to go dt prime. Then we have a rho r prime t prime over, and this is our Green's function, or at least part of the Green's function, delta t prime minus t minus r over c. Okay, when we wrote this when we wrote this expression, and we worked through this this explicitly in this example, and I think, by the way, I think I butchered some of the math there. We didn't really work out very, very carefully what this term actually means. So I just want to label it. So we are the delta function is selecting those parts where this is 0, right? So that means where t prime is equal to t minus r over c, or t is t prime. And now I'll remove this one. T is t prime plus r over c. So we should label this. This is our time under consideration. Under consideration, it's this one. And if we write, if we write this as t prime plus r, but now we're going to actually write out what r is, r prime minus r over c. Then the r vector is the position under consideration, so that's this. All right, so that's the position under consideration. Okay, so that's the position under consideration. And there's some nomenclature here. So so we can actually write this as, so we have a t minus t prime, or t prime minus t is equal to r over c, or c is r over t prime minus t, or basically r prime minus r length over t prime minus t. Okay, so now it should be really, really obvious that we're selecting times and positions that are matching with the speed of light. So because it takes a little time for these signals to get to the point, as well as time in the four-dimensional space-time, such that they will contribute to that integral and they will give you a subsequent potential. It's all satisfied by this consideration that it needs to run, that those signals need some time to travel. All right, so t prime here has a name. So t prime is the retarded time, and sometimes also called t sub r. Now, this is one of those cases where naming is fuzzy, because in my head, retarded time would come after some kind of a starting time, but actually what it means is, so retarded time is just a time some time ago during which that signal traveled from the retarded position, or the apparent position. Where's my, here, the retarded position. That will be r prime. To that position rt, and there it appears with these coordinates. Okay, so together we call this thing ra of t is the apparent position, which is therefore the position of the particle that it had at the retarded time, and we call this the apparent position. Okay. Now, once we put all of these things in, and we're looking at the electric field and a magnetic field of a point charge that's moving with some velocity. So let's say we move some point charge with some velocity v. We're getting an electric field, and the electric field actually has field lines that are kind of squished in a direction perpendicular to the velocity, and they're stretched out when they're more horizontal. Something similar happens if you look at the magnetic field. So this is the electric field. Oops. The electric field. And something similar happens with the magnetic field. You have some kind of a magnetic field, and you get field lines that are, this is a little harder to draw, but that are, yeah, drawing is not super useful. You get magnetic field lines that are going in circles, but they're closer together here and further apart here. Okay. Now this magnetic field is a little harder to visualize, and also what happens relativistically here is a little harder to visualize, because relativistically, so in a frame that is a frame of reference that is co-moving, or moving, a frame of reference in which Q is at rest, we expect the electric field to just be pointing. So now this is at rest. We expect the electric field lines to just be pointing radially out, because at rest we have spherical symmetry. There's really no reason to expect, other than my crummy quality of the drawing, that there's any kind of preference for these field lines pointing in one way or another. So obviously these two pictures are different, and the magnetic field, of course, would be 0, right? So, whoops. So no B field, right? Because there's no current when the charge is not moving, so therefore there's no magnetic field. So hopefully you see that the reason the electric field becomes squished like that is because there is this effect of length contraction. So that's the relativistic effect. So we get length contraction, which literally just stretches the coordinate system. So then instead of having the field lines that are pointing nicely radially out, you get them pointing out sort of more perpendicular to an ellipsoid. So if you want to draw an ellipsoid, so. And actually, if you look at the equipotentials, are actually ellipsoids. All right, so stretched circles. And here, the equipotentials are spheres. Oops. Okay, so that's motivation 1 for wanting to do this, wanting to move into relativity. And so let me make that motivation for relativity and E&M. All right, that's kind of bad. All right, and motivation 2. It's the problem of the Lorentz force, and by Lorentz force I mean just the magnetic field. So let's say we have some kind of a current carrying wire, so some kind of a current carrying wire, and then there's a magnetic field generated. And let's say we take some charged particle Q, and it's moving with some velocity. Then we're going to get a Lorentz force, and that Lorentz force should be, let me see, QV. Hang on a second. Cross products are, yeah. The Lorentz force should be in. So that's your Lorentz force. All right, it should be QV cross B over C. Okay, now big question marks, like where the hell is that cross product coming from? And also, why does this velocity play any role at all? Because there is a frame of reference where, for instance, you could have this current carrying wire, and now this particle is at rest, so Q, but now at rest. Where obviously if V is equal to 0, you would expect the Lorentz force to be 0. But that's not the case, because that force will be there independent of the frame of reference, because Einstein says that things like that are not supposed to change. Our understanding might change, but a force is a force. There's still going to be a force. So what happens is that if you zoom in to this wire, you actually get positive charges that are moving in this direction and negative charges that could be stationary and moving back, for instance. And the difference in speed between the, so let's say V minus the original speed that we needed versus V plus minus V, those two differences are going to be different because V plus and V minuses are not the same. So the amount of length contraction that we're getting is different for the negatively charged particles versus the positively charged particles. And what ends up happening, and at the end of this class, you should be able to actually calculate this. Due to that length contraction, this wire becomes charged. And in order for that to work correctly, I believe it must become negatively charged. And if it's negatively charged, you'll find now a Coulomb force, an F sub C, which is the exact same as the Lorentz force that we were getting, but now we're not getting a Lorentz force because there's no magnetic field anymore, or a velocity to give you that Lorentz force. All right, special relativity. That is. Special relativity. Okay, so before we talk about relativity, let's remember a couple of things from Galilean relativities. So Galileo, right? Galilean relativity. So for instance, let's say I've got some, kind of train track, and kind of a train going this way. There's a train going this way. Okay, now I'm standing here, and I'm playing ping pong. So I've got this ball that's bouncing up, down. So ball bouncing. Oops. And if in a frame of reference where I see the ball bouncing up and down, so I'm stationary, the ball is bouncing up and down, but where in a frame of reference where this thing is actually moving, I see the ball actually doing this. Right? And that is because velocities add. Okay, so V1 is, hang on, V ball is V train plus V ball relative to train, relative to the train. Okay, so that's Galilean relativity, right? Velocities just add. Furthermore, if I take this ball and I throw it, so I throw it with some speed v, then if that's the speed of the ball with respect to the train, and now I look at it, and I have some observer here, standing here, say looking at what that ball is doing. The ball is obviously moving at a higher speed because it's the speed that I threw the ball with is in relation or relative to the train. So then afterwards, if you want to know the speed of the ball in relation to the tracks, you just add those two speeds together, and then things should work out. Okay, so this works really well when speeds are low, as you all know, but this stuff kind of breaks down when speeds are high. So famously, This does not work. When speeds become comparable to the speed of light. Okay, so so what do I mean? Well, okay, so now we're doing the same thing, but now instead of throwing a ball, we're actually we're shining a flashlight. So I need another color. I think it's time to whip up my purple. Okay, so flashlight, ray of light. This is light. And now I see the same ray of light going to the right. And a ray of light here will have a speed c, speed of light, with respect to the tracks. So you would expect, sorry, with respect to the train, you would expect that this here would be the speed of light plus the v of the train, except that is wrong, as we know. Right, so famously, Michelson-Morley experiment tested this using using Earth's motion in relation to the sun, and figured out that actually the speed of light is just the speed of light independent of your speed with respect to the source, because the speed of light is the speed of light. Okay. So node number one, L is L for both observers. So they will not disagree on what the distance between the mirrors is. All right. So setting this up is a little weird always, because we're not used to thinking this way. That relativity of time and space. So the first thing to note is that so I already alluded to the fact that we're going to get length contraction, but we're not really using that yet. Notice that that distance between the two mirrors is independent of that speed v. So both observer 1 and observer 2 will measure the same distance between the two mirrors, because that distance is measured perpendicular to the motion. So they will not disagree on that. Now the thing that's obviously messing with the messing with our understanding is first this part. We're saying, well, whatever that distance is, when we divide it by the speed of light, we're going to call that basically our new delta t prime. Whereas for observer 1, delta t is just L over C. Okay, so then it just becomes a Pythagoras problem. So we have our, this is our Pythagoras, and we'll say, well, the distance traveled, it's, d squared is L squared plus whatever that horizontal displacement is. And then that, by definition, because we're saying that's this is how we define time, is equal to this. And then we divide the whole thing by c squared and plug in our dependence for delta t, which is L over c, and then we get our delta t prime, delta t over 1 minus v squared over c squared. Now that that factor gamma, that's the Lorentz factor. I want to again make this point that this effect is called time dilation. Oops. So this is called time dilation. But it's a little bit of a weird way of labeling it, right? Because the time dilation, the way we're thinking about it usually when we talk about twin paradoxes is that if you're moving with a certain speed, your clock slows down. That's what we mean by dilation, except that's actually not what it says. It says that your delta t prime is going to be bigger from the original delta t for a clock that is moving with the mirror. And because delta t prime is bigger, so that same interval is stretched, we're going to call that time dilation. All right. The twin paradox. So this is a well-known thing, right? So you got Earth here, continents. All right. Got twin A over here, and then twin B takes off, goes off to let's say Alpha Centauri at massive speeds. So let's call it 0.99 C. And let's say we call this distance, I believe it's 4 light years, 4.2 light years. So the question is, twin B goes to Alpha Centauri and then, decides that it's kind of a boring place and, just turns around and heads back. And then comes back home and then meets up with his or her twin brother / sister, and has not aged nearly as much as the person that stayed on Earth, right? So that's the time dilation paradox. So the calculation goes as follows. Well, we have the time it takes for B from the point of view of A, so that's the frame, let's call that frame S, in which Earth is stationary, not moving. Well, the time it takes, it's going to be 4.2, it's 4.2 light years over 0.99 C, right? So that becomes C. So that's 4.2 times, so this is 1.01 is, let's call it 4.28 years. All right. Now, also, they figured out a way to really reverse course really quickly. So it comes back, 2 times 4.28 years. Okay. Now that's the time that has passed as for this person. Now this is what we call delta t prime, because this is what we have as the as the delayed time. Now the actual time that the twin brother experiences is going to be shorter, because it's going to be the square root of 1 minus v squared over c squared times, let me see, 2 times 4.28 years is, okay, that is 1 minus, like I said, 0.99c, right? So that's 0.99. To 4.28 is, yeah, all right, 0.2 times 4.28. So not nearly as much. Actually, I'm missing a square here. It's probably closer. Yeah. Then I cannot do it without a calculator. So somebody run those numbers. So it's 1.2 years. So significantly shorter. Now, there are a couple of subtleties to this. First off, why did we assign delta t prime and delta t the way we did? Well, delta t is always used in these kind of cases in a frame of reference for which two events are occurring in the same frame, right? So the two events are, let's say, leaving Earth and then arriving at Alpha Centauri. And because they're occurring in the same frame, we're using the delta t for it. And therefore, we're calling this the proper time. Now, so that's two events occurring, in the same frame. The second tricky part is that we're saying everything is relative, right? So what distinguishes person A from person B? From the point of view of person B, Earth is moving away from him or her at a speed of 0.99 c. What makes you think that that person is special, right? Now, this becomes very, very tricky, because there's also in relativity, there's also this concept of reciprocity, which actually makes it even a little bit harder to observe this when you also start paying attention to the finite time it takes for things to travel. But really, in this case, there cannot be any ambiguity, because person A actually was always in an inertial frame that didn't actually move. Person B actually had to accelerate, and that's the thing that made him special or her special. Okay, so of course the frame of reference is the same, occurring in the same frame at the same point, right? Because it's in the spaceship. Okay, now the other thing that's tricky about this is that so these the twins, they actually will disagree on how much time has passed, and in fact they would both be correct in saying no, I got, I only aged by 1.2 years, and I aged, the other person says by, what is it, 2 times 4.28, let's call it like 8.5 years, and they're both right because they actually age that much, right? So nobody's particularly more right than the other. But they disagree on how old they got, but they actually do not disagree on the speed that they had relative to each other. So if they don't disagree on speed, but they disagree on time, therefore they must also disagree on distance. Okay, so they do not, let me actually go back to a different color. They disagree or actually experienced different delta t, but do not disagree on their relative velocity. So therefore, the distance between Earth and Alpha Centauri is shorter for B by that same factor, by, and that distance is shorter, and it also means that the spaceship is shorter, right? Because you could imagine that B is basically measuring the distance in terms of, you know, how fast his spaceship is moving past certain points of reference, you know, cosmic dust or whatever it is. So you're measuring it in units of spacecraft length. Then you're going to determine that the distance between Earth and Alpha Centauri is it's changed, and that is the effect of length contraction. Okay. Now there's also a proper length, which has a similar definition. I'm just always proper length, which has a similar definition, but I'm always blanking on exactly how the how they're related. But if you keep this in mind, this example in mind, it should be very obvious because they don't disagree on speed. Once you have delta t, you can figure out what the length is. All right. So another example. This is a famous example. So again, we've got Earth. Well, it's actually not as elliptical. So it's Earth. And now we have, you know, continents. And we are constantly being bombarded with high energy radiation. And as part of that process, there are actually muons being generated. So if we zoom in here, there are actually muons that are created here. And muons actually travel with a massive speed, let's call it 0.98c, towards Earth. They're actually created at, let's say, 10 kilometers. So 10 kilometers above Earth surface. But they're going so fast that they actually make it to the surface of Earth, because actually it turns out muon lifetime is not enough for a significant fraction to reach Earth surface. Without time dilation and length contraction. Okay, so how does that work? Well, so from an observer on the surface of the Earth, it looks like the internal clock of muons slows down, and because it slows down, therefore enough of them survive and reach the surface of the Earth, and that's what we mean by, you know, time dilation. Or in a frame of reference for moving with the muons, they're being generated at 10 kilometers above the surface of the Earth, but then travel with a massive speed towards the surface of the Earth. But to the muon's point of view, that distance traveled is not as long. It's contracted heavily. I forgot what the number is. Instead of, I think it's 2 kilometers instead of 10 kilometers or something. And because it doesn't have to travel as long, it doesn't really take as long. So therefore, it actually survives. So both points of view are equally valid, and both points of view are equally describing that you will find muons on the surface of the Earth that is consistent with the scatter rate and the incoming amount of radiation. And without time dilation, this would not work. Okay, well, ladies and gentlemen, that's as far as I wanted to take it with respect to relativity. So read up. This is it's going to look a little different from what you're used to, because probably beyond what we just talked about, you probably haven't really used much of relativity, and we're going to need a little bit more math. But it's gonna be a lot of fun, and I trust you're going to have a blast. So that's all I had for now. And if you have more questions, stay around for office hours as usual. Otherwise, I will see you on Wednesday. Thanks, everybody.